Welcome. We'll be taking a look at the lesson entitled Factoring Patterns today. And with this particular lesson, I'm not trying to reinvent the wheel. You've done factorings from Algebra 1 to Geometry to Algebra 2. And so all I'm trying to do is create one lesson where we see all the patterns come together and try to solidify some of your skills with that. So let's dive right in. So number one, the first factoring pattern. And apparently it's pretty important because if you notice, I bolded it, I capped it, I threw an exclamation point behind it. So when you are looking to factor, any context for factoring, the first thing you look to do is to take out a greatest common factor. So if you remember what that means, and I sort of word it this way, the greatest common factor is really just the reverse of the distributive property. So you all know that distributive property means you multiply into the parentheses and put it in standard form. Well, with the greatest common factor, you're pulling out the GCF and then creating your parentheses to see what the remaining factor is. So the reverse of the distributive property. And as it says, can't stress this enough, no matter what type of factoring you're doing, before you try any other pattern, look to do this first. If you can do it, great. If you can't, then you'll try to resolve it with using another pattern. Okay, so let's get example one taken care of. So example one, factor each polynomial, pretty straightforward. And if you notice, we've got two terms separated by that minus. This would be a quartic polynomial written in standard form. And what we're going to try to do is write it as a product of its factors. And so I look at these two terms, and I'd ask you very lightly, I don't know if I can do it lightly, but you guys very lightly on your paper, can you circle the two terms separated by that minus? And mentally, what we're thinking to ourselves is there anything that's common to both of those terms? Are there factors that go into 12x to the fourth and also 30x squared? So I look numbers first. Numerically, it looks like the 12 and the 30, that there's a 6 that can be pulled out of both of those numbers. And then I look at x to the fourth and x squared, and it looks to me like x squared can be pulled out of each of those terms. So my GCF is 6x squared, 6 times x times x. Then I make my parentheses, and I have to see what's remaining. So I'm going to do this a very particular way here because it's going to help us with the last example on this lesson. But if you know it and you want to just move on, by all means, please feel free. So I always work left to right. And I always ask myself with the GCF is, did I take some of that out or all of it out? And if I look, I had a 12 and I took 6 out. So I took some of the 12 out. But I hope you'd agree I still have a factor of a 2 there. And then I keep going to the left to right, and I have x to the fourth, and I took out x squared. So did I take some or all of the x to the fourth out? Well, I only took some of it out. I only took x squared out of it. And so I still have some x's in there. I have x squared left in there. And then minus. Did I take some or all of the 30 out? Well, I only took some of it out. I only took a factor of 6 out. So you still have a factor of 5 in there. And then did I take some or all of the x squared out? Well, I took all of it out. There it is. There's the x squared. So I took all of that out, and so there are no more x's inside. And so, again, if it feels weird for me to talk about some or all of the factors, don't worry too much about it at this stage, but we're going to see some more complicated versions of these at the end of the lesson, and I think that will be helpful. So I'm going to erase this part now, but because it's tough for me to lightly circle these terms, but you guys can kind of do that on your paper, just lightly circle. All right, let's move on to letter B. So same idea, guys, two terms separated by that addition symbol. Let's see if we can write it as a product of its factors. So here's one term. There's the other term. So again, very lightly on your paper if you would. And here's what I'd ask you. What is common to both those terms? This is an interesting one. And the reason I put this on here is because we'll see this come out on the back side as well. All right, did you decide what is common to both those terms? If you notice, I've got an x plus 3 in this term I circled, and I have an x plus 3 in this term I circled. And so as a result, everybody, I think we're going to pull out that x plus 3. So it's not a monomial like it was over here. It's what's called a binomial. but that is the greatest common factor. And so you ask yourself essentially, when you pull out that greatest common factor and then you create your parentheses, what's left inside the parentheses? Well, I took the x plus 3 out, but I haven't touched this at all, so there's still x squared. And then here's the plus, and then I look at the second term and I say, well, you know, I took this x plus 3 out, but I haven't touched the 5, so that's still in there. And so you see it ends up being one binomial times the other. Excellent. So before we move on to pattern number 2, the moral of the story is when you factor, always look for the greatest common factor there. Pull it out, see what's remaining. Keep that in mind because it's going to get quite a bit harder towards the end of the lesson, but the same ideas will unfold. Okay, let's go get number 2. Number 2 would be the quadratic trinomials. These are the easier versions with just a single x squared, so kind of a 1x squared out in front. And again, not trying to reinvent anything here. So this is what's called the reverse of foiling. So if you remember foiling, first, outside, inside, last, this is sort of reversing that process. And what you're going to look for here, everybody, you're going to look for two numbers that multiply to c, so multiply to the end value, and add to b. So add to the middle value. So here you kind of see the b value and the c value in that trinomial expression. Awesome. If you can do these, great. Move it on forward. If you'd like a little run through, that's what I'm here for. So just to be quick on letter A, if you remember, I'm looking for two terms that'll multiply to x squared. And so that should be just x and x, right? And then here's what I put in this piece, in this line right here. So to figure out what goes on the back ends, I'm looking for two numbers that multiply to c and add to b. So multiply to negative 18 and add to 3. And I hope you'd agree that it's got to be a positive and a negative, and it looks like plus 6 and minus 3 would do the trick. Now if you're ever unsure with this reverse foiling, just FOIL it back out. X times x is x squared. X times negative 3 is negative 3x. 6 times x is 6x, so negative 3x and 6x make positive 3x. And 6 times negative 3 is negative 18. So that's our winner. All right, let's see if you can do letter B all by your lonesome there. I'll get it going, just kind of thinking about it, but either pause it or just go get it. But ultimately here, it's going to be x and x, and I'm looking for two numbers that'll multiply to positive 40 and add to negative 13. So we do know it has to be minus minus, right? Just good number sense. Has to multiply to a positive number, but it also has to add to a negative number. And it's going to be minus 8 minus 5. By the way, order doesn't matter here, so if you happen to have written x minus 5 and x minus 8, same thing, of course. All right, that is pattern 2. The question, though, is can you do pattern 3? So pattern 3 just takes it up a notch. And here's what I'd have you do. Just underline that little a. So that's all the difference. But it makes it harder when we have a number other than 1 in front of that x squared. So what we're going to write in here, of course, reverse the FOIL. No doubt about that. Okay. Now there are a couple ways to do this, and maybe your Algebra 2 teacher kind of taught you another way as well. And look, as I said, whatever works for you, please use. I'm just trying to give you different ways to think about it, and if it works, great. So there are a couple ways to go ahead and factor these types of quadratic trinomials. The first, if you have really good number sense, is just trial and error. You can really kind of see the outside and inside combined to the middle term, and you can get it pretty quickly. Now I guess I'm gloating a little here, but I've got a really nice method that I will show you, and it's pretty foolproof if you just kind of follow it from beginning to end. So I will show you that as well, and maybe it'll work for you, and if it does, wonderful. And if you can just do it without using it, also great. So let's kind of start out letter A, And let's just do the idea of trial and error, right? So you do know a quadratic trinomial is reverse foiling, so that means just two binomials, one there and one there. And remember how it works. If I'm reverse foiling, the f relates to the first. So I need a term here and a term here that are going to multiply to the first term in this quadratic trinomial, 2x squared. Now the nice thing about this one in particular is it can only be 2x and x, right? And for our purposes now, the order doesn't necessarily matter. Now the back end is where it gets a little tricky, because what we're looking for here would be two numbers that multiply to -6. So something here and here that has to multiply to -6. Now the catch is getting the outside and the inside to combine to a -1x. I'm going to just put a little -1 there just for our purposes. And that's the combination that we have to create. So we need two numbers that will multiply to -6, but then also have the outside and inside combined to -1x. So, I'm just going to work off to the side for a moment. It could be a 1 and 6 situation or a 2 and 3 situation. And at least they're not a ton of factors to try. So what you might do is be like, well, maybe 1 and 6 work. And so I try a 1 there and a 1 there. And even before putting in signs, I'll at least see if it's viable. And, I look at this and I say, well, that has to be a 12x, the outside, and the inside has to be a 1x. Is there any way for 12x and 1x to combine to a -1x? No, of course not. And so as a result, you know right away that the 1 and 6 combo is simply not going to work. So then you come back and you try another combination. And you might say, well, maybe a 3 and a 2 situation or something like that. And then I at least just get a sense of, is it even possible? Well, the outside would be 4x. The inside would be 3x. It's got some promise because I can make 4x and 3x equal to -1x. Probably a minus there and a plus there. And would it work all the way through? I did need -6 on the back, so +3 times -2 is -6. And outside and inside do combine. And so I think that's your winner. Okay, that's great. That's trial and error. And again, when you get good at it, it runs through pretty quickly. I'm going to show you my method. And so here's how it works. I'm going to actually start from the very beginning. And I'm going to do my method on these guys too, just so you see it 2 more times after this. And then hopefully you will have perfected it by then. And again, if you like it, great. And if you don't, no harm. I'm not offended at all. Okay, so here's how it works. We take this a value, and we actually bring it on over to the last term and multiply those together. Because I don't like that 2. It's kind of bothering me. So what I'm going to do, at least at the beginning, is bring it on over, and 2 times 6 is 12. So here's my -12. Now this is something I can factor pretty easily, right? It's not a problem. I know it's x and x. And in fact, guys, you're going to leave a little room in front, but it is x and x. And I need two numbers that multiply to -12 and add to -1. So -4 and +3, that's not a problem. But obviously, guys, if I FOIL this out, am I going to get the original polynomial that I wanted to factor? No. What I needed was for two terms to multiply to this 2x squared. The problem is I don't know where the 2 goes. And so here's how we fix it. I actually put a 2 in both of them. So you see why I left a little room there. So the 2 goes back in both. But the problem is, if I ask you to multiply the firsts out, 2 times 2 is 4. It's not 2. So something's wrong here. I accidentally put in an extra 2 in. So what we do, guys, to fix that is we divide each factor by whatever number goes into those numbers inside the parentheses. For example, 2 goes into both 2 and 4. And so when I divide each of these by 2, I hope you see, guys, I get x minus 2. Now, really only 1 goes in. Not that I necessarily need to do that, but nothing goes in really to 2 and 3 other than 1, so there we go. And do you notice? Same thing. And that's how it works. Cool, right? Let's go get letter B. So I'm just going to show you my method. If you can do it another way, by all means. So I bring the 15 on over, and I get x squared minus 11x plus 30. Awesome, because that's easier for me to factor. So now what I do is I just set up my two binomials. I'm going to leave room in front, but I do an x and an x. And I'm looking for two numbers that multiply to positive 30 and add to negative 11. So it's got to be minus minus, and it looks like it's going to be 6 and 5. Cool. But I don't stop there, guys, of course, because I need to multiply out to this polynomial, not this one. Well, I need the front parts to get to 15x squared, so I don't know how that's going to play out just yet. So I put a 15 actually back into both parts. Obviously, that's not right, because 15 times 15 is 225, not that. Okay, so I've got to divide out the extra. So you look at the parentheses here, and you just ask yourself, well, what goes into these two numbers? Well, 3 divides evenly into 15 and 6. So if I divide both of those by 3, 15 divided by 3 is 5, so that's 5x. 6 divided by 3 is 2, so 5x minus 2. And then I look over here, and I ask myself, well, what can be divided into 15 and 5? And I hope you'd agree, 5. And so same idea, 15 divided by 5 is 3, so that's a 3x, and then minus 1. Now if you're ever unsure if you did it correctly, remember, just FOIL it quickly out. Now I know the first and the last do work, but let's just quickly check the outside and inside. The outside would produce a negative 5x. The inside would produce a negative 6x. So negative 5x, negative 6x make negative 11x. That's your winner. You know, it'd be great if you could do this last one all by yourself, trying my method or trying anything at all. But if not, no biggie. All right, I'm going to go through it one more time for you. The 10 goes over. 3 times 10 is 30. I definitely factor that. Leave room in front, but basically it's x and x. I'm looking for two numbers that multiply to positive 30 and add to negative 17. This is a good one. Actually, it's minus 15, minus 2 would do the trick there. Now again, I've got to put the 10 back in, but obviously I made a mistake because 10 times 10 is 100. So I have to figure out what is extra in terms of numerical factors that need to be eliminated. And so I look what goes into both 10 and 15. Seems like 5 does. So that would be 2x minus 3. And same thing here. I look at the 10 and the 2, and it looks like I can divide each of those by 2. And there we go, 5x minus 1. If you're not convinced that it does work, FOIL it out. And remember, you're always trying to get the original. Okay. Very good. I think we're ready to move on to the next piece. So, example 4. It says, what do these quadratic trinomials have in common? And then we'll fill in a blank or two. This one I do want to be rather quick on. We're going to see these types of polynomials come up and how they're factored, so I just want you to get comfortable with how they are written. I'm going to take a moment and just factor all 3 for you very, very quickly. And if I said factor this, you would say x plus 3 times x plus 3. If I said factor this one, you would say 3x minus 1 times 3x minus 1. And lastly, if you wanted to factor this, you would do it as x minus 5 times x minus 5. So take a look at your answers here and maybe compare them to the answers above. And what do you notice is maybe a little different with these particular answers? And I'm hoping you've noticed that it just so happens that the factors are the same, right? X plus 3 times, well, the same thing, x plus 3. And so the question is, can you write it in a slightly different, more compact way? And again, I know you've seen this before, but basically it just means x plus 3 squared. So kind of get used to writing it that way because you are going to see this come to fruition in several lessons over the course of the semester. So this 3x minus 1 times 3x minus 1 is really 3x minus 1 squared. And lastly, this should be x minus 5 squared. All right, cool. So obviously, as we see this in a particular context over the semester, you'll hear me call it by a particular phrase. So let's get comfortable with that piece. Each of the original problems were what are called perfect square trinomials. And I won't go into all of the details as to why that is. But you do see perfect squares on the front and on the back, and then there's something with the middle term too for this to work. But they are what are called perfect square trinomials. And getting a little lazy here, but every perfect square trinomial factors into what is called the square of a binomial. Okay, because you can see, here's the binomial, and it's squared. Awesome. So I want you to be able to recognize that and also express it as you see on your paper. Cool. Let's go get the fourth pattern now, what's called a difference of two squares. So this one does come up a little more often than you think, so let's see if you remember how to pull this off. So when you have one squared minus another squared, you can factor it in two binomials, and it factors into what is called the sum and difference pattern. So a plus b times a minus b, essentially the square root of the first term and the square root of the second term, 1 plus, 1 minus. And again, I think I called it sum and difference pattern. Perfect. Let's see it in action. So a lot of factoring really comes down to two things. It comes down to recognizing a pattern, and then it comes down to applying the pattern. So first thing you always do with factoring is see if there's a greatest common factor, and I don't see that. There's nothing that goes into x squared and 64. It's not a trinomial, so it doesn't kind of fit the last few things that we've kind of talked about there. But it is what's called a difference of two squares. That's a perfect square. 64 is a perfect square minus in between. And so when I recognize that, then I get my two parentheses set up right away. What times itself would give us x squared? Has to be x and x. What times itself will give you 64? Happens to be 8 and 8. And the reason there's no middle term is because the outside and inside cancel. And the reason they cancel is because one of them is the negative and one of them is the positive when we do outside and inside. So I hope you see that. It's still reverse foiling, but you're getting the outside and inside to cancel. Perfect. So recognition and then application, those are the keys. So 25x squared, perfect square. 36, perfect square. Minus in between, we're ready for it. So what times itself would give you 25x squared? Must be 5x and 5x. What times itself would give you the 36? 6 and 6. 1 plus, 1 minus. That looks great. And by the way, I always kind of like boxing up final answers, so let me do that, and let me do that. Perfect. Now let's move on to letter C. Interesting one here, a little harder. And if I recognize this one, hopefully you do from Algebra 2, but anything to the fourth power is actually also a perfect square. So this is also perfectly a difference of two squares. So with that stated, I get my two parentheses ready to go. Now this is a good one. What times itself is x to the fourth? Well, it has to be x squared times x squared. That looks great. What times itself is 16? Well, it has to be 4 and 4. To get the outside and inside to cancel, 1 plus, 1 minus. That's great. Now, there's a reason this is such a good one. It just so happens this can't factor any further. So I'm going to bring it on down. But as I look at this, The idea is that the light bulb goes on and you recognize, hey, wait a minute. That's also a difference of two perfect squares, right? That's a perfect square. 4 is a perfect square, minus in the middle. So it can be factored even further. So that's the other thing that comes with factoring is once you do one particular pattern, look to see if you can go further. And so in this case, x and x would go here and here. What times itself is 4? Well, it's got to be 2 and 2, and then 1's plus, 1's minus. So that happens to be your final answer. And maybe at this stage you're thinking, hey, wait a minute. What about that x squared plus 4? Can that be factored? And I would ask you to try to set up two binomials that can create x squared plus 4 if you were to multiply it out. And I don't think you can. And so as a result, here's what I want you to put in. I'm going to put it in up here. You put it in on your paper wherever is appropriate. There is a difference of two squares, no question about it. But there is no sum of two squares. So did you notice that over here? These are perfect squares, but it's a plus in the middle as opposed to minus in the middle. And when that does happen, that is prime. You cannot touch it. Okay. And again, if you think you have something that you want to check with me, by all means, and I'll shoot down your proposition. Okay, let's go get pattern number 5. This is a little more obscure, but you did see this in Algebra 2. So remember, there's a difference of two squares, but no sum of two squares. There is, however, both sum and difference for two cubes. So just remember your cubes real quick. I'm going to put them here for you, being the nice guy that I am. 1 cubed is 1. 2 cubed is 8. 3 cubed, excuse me, give me one sec. 3 cubed is 27. 4 cubed is 64. 5 cubed is $1.25. 6 cubed is 216, ... on that. So maybe that's helpful for you as you look at these. Now, for this one, I'm going to just follow the patterns that you see. Here's what's called the difference of two cubes. Here's what's called the sum of two cubes. And you see that it breaks down into two factors, a linear factor and a quadratic factor. Small linear times large quadratic. So that's how we're going to play these out. I'm just going to follow suit, and I'm going to give you a couple little hints and suggestions as we go through it. So we'll do 3 of these. Hopefully the first one you'll be like, all right, I start to see how this matches up with what's on the board. But by the second and third, hopefully you can kind of do them a little more independently. So looking at A, what I want you to do right off the bat is get a little linear going and a larger quadratic going. And here's how it works. The nice thing about the linear version of this is it is just literally the linear version of what you see on the board here. So basically it's just the cube root of this and the cube root of this. So the cube root of x cubed is definitely x. The cube root of 8, as we know, happens to be 2. If that's a minus, that's a minus. So the way I would phrase it, and it's maybe not the best way, but I like it, it's the linear version of this right up here. It's the cube roots of what you see. Perfect. Now the quadratic is the one we've got to muddle through, and I'm going to walk you through a couple parts pretty easily and then give you a trick for the middle part, which is right there. So remember, factoring and multiplication go hand in hand. That's what it's all about. So think of it this way. X times something had to give you this x cubed right here, right? Because this is multiplication. So x times what would give you x cubed? Well, it's got to be x squared, right? On the back end is where we would have -2 times something would have to give you the -8. So everybody, -2 times what would give you -8? And I hope you'd agree, -2 times +4 would give you -8. So that's where these two terms come from the firsts and from the lasts. Now everything else, interestingly enough, when you do the multiplication, cancels out. And the reason is this middle term right here. So here's the trick. I'm going to write the trick first, and then we'll get the answer. So the trick is looking into the linear factor. And so you're going to multiply the terms in the linear pair. But then you're going to do the opposite sign. So here is what I mean by that. So we take the two terms that are in the linear pair, right? The x and the 2. And we just multiply them together. X times 2 is 2x. So that's what goes here. If that is a minus, this is the opposite sign, and that's a plus. That's how you know what this middle term is here. If you can get that, you've got it. Okay, let's go get letter B. Recognize, this is a perfect square, by the way, but it's also a perfect cube. So to see really which pattern we'd use, we'd go right here and be like, oh, x cubed. That's not a perfect square, that's a perfect cube. So we know it's the cube pattern. Small linear, large quadratic. Perfect. Now, this needs to be the linear version of that right up there. So cube root of x cubed, again, is x. Cube root of 64 is 4. And if that's a plus, that's a plus. So this is just the linear version of this. And now walk yourself through as best as possible. X times what would give you x cubed? X times x squared. Positive 4 times what would give you positive 64? It has to be 16. So those would be the two parts of the quadratic. Now we have to get the middle, the linchpin of it all. So remember what we did. We take the terms in the linear pair and just multiply them together. X times 4 is 4x. And whatever term is here, whatever sign is here, excuse me, that's the opposite. That's it. Again, I like boxing these things up, so that's looking pretty good. Be great if you can do the last one all by your lonesome. Let's see what we've got. Okay, small linear, large quadratic. Cube root of 8x cubed is 2x. Cube root of 1 is 1. Okay, that's a plus in there. Linear version of that. Now, walk yourself through the quadratic. The first, then this, then the middle. So 2x times what would give me 8x cubed? Well, 2 times 4. X times x squared. Cool. Positive 1 times what would give you positive 1? Positive 1. Now for the middle term, remember, you just multiply these two terms together. Multiply the terms in the linear pair. So 2x times 1 is 2x. If that's a plus, that's a minus. So we did 3 of them. Hopefully by the third one, you get the idea. Hopefully this little trick right here works for you to get that middle term. You'll do a little practice on it to ensure it. Cool. Couple more patterns to work on. They're starting to get a little harder here, as you can see. The 6th pattern is grouping. So let's go give grouping a try. And I'm just going to write down what you did last year in Algebra 2 with grouping. So we group the first two terms together and the last two terms. And it's really just GCF. That's what this comes down to. After we do that, we're going to factor out the GCF. So again, just kind of said that grouping really comes down to greatest common factor. So factor out the GCF from each pair. And I'm going to just write this as well. I think this will be helpful. Include the sign in the last pair. And I'll show you what I mean by that in just a second. Awesome. And then one more time, we have to go GCF. So then GCF, I'll just put again. Again, I'll show you what all that means. If the wording up there is throwing you off a little bit, give it a moment or two if you would. Okay, let's go get example 7. So group the first two terms together and the last two terms together. So that means like this. I do it this way. Maybe your Algebra 2 teacher did it in a slightly different way, and if that works, again, that's totally fine. But we're going to go greatest common factor on this. So I look at x cubed, and I look at 4x squared, and I ask myself, well, what is the greatest common factor of those two? And I hope you'd agree it's x squared. So I take out x squared, and when I do, I get x minus 4. Now here's the key. I look at the last pair, and same idea. I'm looking for greatest common factor, and I hope you see it's 2. But as it says right up here, include the sign in the last pair. So when I see I'm going to pull out a 2, I'm going to actually pull out a plus 2 there. So the way I'm doing that, you have to make sure you pull out that sign. And when you do, it's x minus 4. That's great. Now take a look at that for 1 minute, and that hopefully will look vaguely familiar. So watch this. I'm going to go back a couple boards here to the very beginning. And do you remember this one? Look on your paper right here and look at this, and you can see that that's pretty much the same position. We've got this binomial in both of those terms that we're going to factor out. So now let's go back to it. So if you look at this, I could circle this, and I would encourage you to do that very lightly on your paper. Circle that, and then circle this. And you notice that there's an x minus 4 in each of those terms, and so it gets factored out. When I pull out an x minus 4 from here, I get an x squared left. Here's my plus. When I pull out an x minus 4 from there, it looks like I still have a 2 remaining. So it looks like it's a greatest common factor, exactly like the one that I put on, I guess that was example 1b. So if you need that as a frame of reference, please use it. All right, so if it clicked the first time, great. See if you can get the last two pretty quickly. If it didn't, maybe after the second one it'll work. So here we go. Group, group. Let's factor out of the first two terms here. It looks like an x squared is coming out. I hope you see that. When I factor out an x squared, it looks like I'll get a 3x plus 4. Now here's the key for this second piece. I have a negative 6x and a negative 8. I'm going to pull out the negative here. So in this case, I'm going to pull out a minus 2. Again, include the sign as I have said. Because when you include the sign, I hope you'd agree, then this changes to a positive 3x and this changes to a positive 4. If these two are the same, then you know it can be factored by grouping because that is the greatest common factor to this term and to that term. That's the greatest common factor. So as the greatest common factor, it cancels out. Not cancels out, it comes out there. There we go. Now I've got it. And there it is. I like it. Okay, let's go get this last one. This one's a great one. Okay, so 4 terms. Really the only method that traditionally we can use for factoring would be grouping. And so let's go ahead and make it happen. So looking for x to the 4th and x cubed. Looks like x cubed can be factored out there. And I'd get x minus 1. Now this is the key. This is the reason I put this in place. If you look at this, it doesn't look like we're going to really pull anything out, but we still want to. So if you think about what the greatest common factor is to x and the 1 there, it's really a 1. And so I want you to actually include the sign, like I've always said, and the positive 1. So that's what comes out. Then you notice the x minus 1 still stays in there. But the GCF needs to be pulled out with the sign on that last pair. It just has to be for us to see it. If you don't, it's just really not going to work at all visually for you. Okay? If you want, circle that. Circle this. What's common to both of those? X minus 1. So I pull out x minus 1 from each, and as a result, should get x cubed plus 1 left over. Now before I box this one up, just sort of it's a good little reminder about factoring. Always look to see if you can factor further. So x minus 1 is good. I'm going to bring that on down. But I'm wondering if you've recognized something here. And again, factoring is all recognition and then apply the pattern. This is a sum, here's the sum, of two perfect cubes, x cubed and 1. So we get one more shot at sum of two cubes, which means a small linear and a larger quadratic. I'm going to do this one rather quick. So the linear version of that would be x plus 1. X times x squared is x cubed. 1 times 1 is the 1. Multiply those and different sign, so minus x. If you want to put the 1 there, great. If not, of course, that's fine. And there you go. This is always going to be a prime quadratic, by the way. It's a good question if you had it. Can you go further on that? No. Okay, so we've covered a bunch of good patterns here. Now we get to the above and beyond. So let's take a moment and read number 7. It says factoring involving fractional and negative exponents. Now I'm going to kind of go through this a little slower, and let's see if it works for us, okay? So first things first, it's all GCF. So remember how we started the lesson with GCF? That's what this is. So GCF, let's see if we can put that in properly, of any powers. In the same base, because that's what we'll be looking at here, is the one with the smallest exponent. So write that in if you would, please. And I'll show you what I mean by that. Perfect. Now example 9 is actually the culminating piece, but we do want to take care of example 8 first, because we can't factor it if we don't know what the greatest common factor actually is. So here's the idea. We've got two terms separated by the minus, and I just want to know what the greatest common factor is. So as I look at this term and this term, numerically I look at those two, and immediately I'm thinking, well, 8 goes into both. That's great. Now if you notice, there are powers of x in this term, and there are also powers of x in that term. And so I'm just going to use what I wrote up here. If I'm looking for the greatest common factor in a particular base, it's just the smaller power of the two. And so what's smaller, x to the 3/2 or x to the 1/2? Well, it's got to be x to the 1/2. So that actually is your greatest common factor of these two terms, this and this. Okay, so keep this in mind for sure. Okay, letter B. What would be the greatest common factor of x plus 1 to the negative 2/3 and x plus 1 to the positive 1/3? So two terms, base x plus 1. And if I want the greatest common factor, I don't think too much about it. It's just that base, and it's the lower of the two. Obviously, negative 2/3 is smaller than positive 1/3. And so that's the greatest common factor. So let's see what we can do with the final piece of the puzzle. So these are a little harder now, obviously greatest common factor. Now the question is, can we pull out the proper greatest common factor? And then the key is going to be, can we see what's remaining inside the parentheses? Notice what it does say. Write your answers with positive exponents only. So when we have negative exponents and they get, they're in our answers, we have to put a final answer with positive exponents only. Okay, so we've got two terms, that one and that one, separated by the minus. I'm going to do a little greatest common factor on it, and I would ask myself, what goes into both 6 and 12? I pull out the 6. What's the greatest common factor of x to the 3/4 and x to the 1/4? And it has to be the smaller of the two, so x to the 1/4. And I make my parentheses. Now here is the thing. I don't know if you remember, but at the very beginning of the lesson, I sort of talked about sum or all. So as you work left to right, that's what you're going to ask yourself. Did I take some of the term out or all of the term out? So I'm going to just write that here. I would encourage you to do the same. So when I actually express it in those terms, it'll make pretty decent sense. So here's how it works. I start here, and I ask myself, did I take some or all of the 6 out? And I took all of it out. There it is. Then I go here, working left to right. Did I take some or all of the x to the 3/4 out? Well, I took some of it out because I only took x to the 1/4 out, which means right away I have more x's in there. I have x raised to the something inside the parentheses. Now to figure out what it is, it's all based on just quick division. So guys, what you're going to do is take the original and you're going to divide what you pulled out. Okay, and you do this intuitively with easier stuff. This is just a more formal way to look at it. So I know it's x to the something. And so when I do this division, the original divided by what I pulled out, I know I keep the base. And do you remember what you do to the exponents here? I subtract them. So what is 3/4 minus 1/4? It's 2/4, or 1/2. And so that is what goes inside here. Cool. Here's your minus. Now keep going left to right. Did I take some or all of the 12 out? Well, I only took some of it out. And what do I have left? I have 2 left. Then I end right here. Did I take some or all of the x to the 1/4 out? I took all of it out. So there are no more x's inside. And that, oddly enough, is your answer. Okay, maybe it made sense a little bit. Again, practice is going to make perfect with this type of stuff. This is now raising the bar a little bit with factoring. All right, let's go get the next one. So, 2 terms separated by that minus right in the middle. And if you notice, each term has a base of x plus 3. So when I talk about the greatest common factor, I know it's going to be x plus 3, and it would be the smaller of the 2 powers. So which is actually smaller, to the negative 1/2 or to the negative 3/2? And in this case, it's to the negative 3/2. So that's my greatest common factor. That's pretty hard. And then I see what's left. So watch what happens here. This is a good one. So think of it this way. This is smaller than that, right? So the question I have for you is, did I take some or all of the x plus 3's out? And if you look, I only took some of them out because I took out to the negative 3/2, but that's to the negative 1/2. So which means, everybody, I still have some x plus 3's inside there. The question is, what is that x plus 3 raised to? So I would do the division, just like we did here. But ultimately, I know it's going to be x plus 3 to the something. To figure out what it is, I subtract the exponents. Let's see if you can do this. Negative 1/2 minus negative 3/2. So negative 1/2 minus negative 3/2. Subtracting a negative is just like adding a positive. So negative 1/2 plus 3/2 is actually 2/2, which is 1. So which means, everybody, this is just x plus 3 to the first. Anything to the first power is just itself, so x plus 3. That one's a good one. Cool. And then minus, now here's an interesting one. Did I take some or all of the x plus 3's out here? I took them all out. There they all are. But there is at least a factor remaining here. You know, this times something has to give me the original, and it's times 1. Does that make sense? Because you're just reverse distributing. So if I was to distribute, that would be this right here. Now 2 things happen. X plus 3 to the negative 3/2 times, and this is x plus 2. Awesome. Don't forget though, what did it say? Write your answers with positive exponents only. So we've done this in a previous lesson. If it has a negative exponent, how do I resolve it to make it positive? In this case, it's going to go to the denominator. That's some pretty good math right there. I like it. There you go. Okay. Again, this one, it's going to really help if we do some practice with this. Let's try this last one together. So, two terms separated by that addition symbol right here. Let's look at the greatest common factor. So I look at the coefficients, 2 and 4. Let's take out a 2. I take a look at the powers of x and x squared. What's the greatest common factor of x and x squared? X. And then I have a 3x plus 4 to the 2/3 and a 3x plus 4 to the negative 1/3. I know that the greatest common factor is the lower of the two powers, so that would be negative 1/3. That's your greatest common factor. Okay, now, big parentheses. Let's fill it in and see what happens. So do the sum or all trick. I think it's going to work for you. Just work left to right. Did I take some or all of this too? All of it. So there's not a 2 in there. Did I take some or all of the x? There it is. I took all of it. So no more x's there. Did I take some or all of the 3x plus 4 to the 2/3? Well, I took some of it out, right? Because I took out to the negative 1/3. I had to the positive 2/3. So what that means to me, everybody, is that there's still some 3x plus 4s inside, because I only took some of these out with this. So to figure out what it's raised to, I divide these two, which means I had 3x plus 4 raised to the something. So I'm going to do subtraction on the exponents like I did last time, 2/3 minus negative 1/3. And these are all going to work out pretty cleanly, guys. Shouldn't see too many issues. But I think you would see that it's raised to the first power. So this would be really 3x plus 4 to the first, which is just 3x plus 4. Cool. And then here's my plus. Again, just continuing left to right. Did I take some or all of the 4 out? Well, I took some of it out. I took a 2, so there's still 2 in there. Did I take some or all of the x squared out? Well, I took some of it out, because here's an x right here, but there's still an x remaining. And did I take some or all of the 3x plus 4 to the negative 1/3 out? I took all of it out. There it is. So there are no more 3x plus 4s in there. And now, everybody, we just play cleanup. So I have 2 times x times 3x plus 4 to the negative 1/3. And if I clean up inside the parentheses, just combining like terms, 5x plus 4. Is the answer good? Yes. Is it perfect? Well, not according to the instructions. Positive exponents only. And so does everyone see this right here? We've got to fix it. So the 2 is fine. The x is fine. That 5x plus 4 is fine. But the 3x plus 4 to the negative 1/3 comes to the denominator and now is a positive 1/3. And there you go. So I hope you focused a lot of your attention in this lesson just on the last piece, because that's where the pre-calculus level kicks in. If you have some questions on the way I explained it, obviously we can look at some together. But thanks for listening. I appreciate it.